Okay, long time no see, guys. I was a bit negative in the last session, so I apologize for that. It's a little early, but I'm going to give you a positive vision for where Ethereum should go. Disclaimer that this is some early stage work. We're working on this with Malesh Pai, who is a professor at Rice University, currently on leave, working with us at ConsenSys SMG. Alberto Sanino, who's at Miston, and Joaquim, who's at A16Z, who will be at, I believe, Technion next year, or maybe in 2 years. I think he has a 2-year postdoc at A16Z, and then he'll be at Technion. The thrust of this is basically blockchains, as we know them, are fundamentally broken, because most blockchains in production are driven by this leader-based paradigm, which is there's only one person who's allowed to contribute and add transactions to the blockchain for whatever slot time is decided by the network. So on ETH, that's 12 seconds. So right now, there's only one person who, if I submitted a transaction, could include it on the chain. So that single leader is going to decide what goes in the block and also in what order, although I think that's less important. And the power of that monopoly, you see I'm wearing it and the proposer monopoly shirt, so you can probably see where I'm going here. The power of that monopoly is exactly what we know and call MEV. So there was a post that Dan Robinson and Dave White put out a few months ago that said priority is all you need. So there's two things that the leader can do with its monopoly. They can reorder you, or they can censor you. Reordering would be moving you around within the block. Censoring would be leaving you out altogether. And the claim in this priority is all you need post is basically, if we ordered transactions based on the priority fee, then there's a bunch of stuff we can do where the apps read which priority fee, charge additional fees based on that, and you can get a lot of interesting mechanisms that are helpful for building MEV-resistant applications. But the problem is, even if you do that and you don't have censorship resistance, then the priority ordering kind of falls apart. Because something that's should be priority ordered before something else can just be left off entirely, censored, and then it breaks all of the guarantees that you might want to see with your priority fee mechanism. So I am not the first to say this. In fact, Vitalik was quite early on this one. In a 2015 blog post, he described censorship. And you might be familiar with censorship as like OFAC transactions, Tornado Cash not going on. In 2015, Vitalik was talking about the Silk Road. But there's another part that we don't often discuss, which is censorship resistance is important for credible neutrality for the operation of financial applications on chain itself, basically. And this is the point that Vitalik made in this post is, it's not just for Silk Road transactions to make it on chain, which is a lot of what's other people who are working on censorship resistance are optimizing for. It's actually, you need same block censorship resistance for the functioning of financial systems. And in 2023, myself, Elijah Fox, and Malesh Pai, who's one of the co-authors on BRAID as well, we wrote this paper about running on-chain auctions without censorship resistance. So we made the point that it's very hard to hold an auction on chain because if you hold an auction on chain, you might have a $1,000 item, for example, and then the proposer ends up running the auction themselves because any bids that come in get censored, and the proposer submits what's called a stink bid for like 1 cent, and they can win the auction for 1 cent. And so we kind of made this point. We were working on LVR reduction at the time, which is one of the main sources of MEV, as I just said in the chat with Tessa, and we're going to try and fix it, basically. So like I said, a lot of the other proposals on Ethereum are trying to get the Silk Road style of censorship resistance, which is slow, which is not for financial applications, and in my opinion is useless, basically. Because you can get censorship resistance for your Silk Road transaction if you want. Just pay a slightly higher fee. In fact, you can buy out the whole block if you want on PBS and include just your transaction. In fact, like the censorship resistance for tornado transactions, I think, is not super important, and it's certainly not something that we should introduce a bunch of additional latency, rounds, complexity into the protocol to solve. Because we didn't build ETH so that like North Korea can transact on Tornado Cash. We built ETH so that we can put decentralized financial applications on chain. And so this talk about BRAID is basically an approach that tries to provide short-term censorship resistance in the current block for financial applications, whereas these other proposals for inclusion lists are more focused on non-financial applications. So let me give you a quick definition of of this economic censorship resistance, the short-term censorship resistance that I'm talking about. We think of a blockchain as this abstract public bulletin board, which has two operations. You can write by sending a message, M, with a tip T, and that would write the message to the chain. And you can read, which will return a list of all the messages that have been written there. But the kind of wrinkle here is that this write operation might fail. Why might it fail? Because there might be an adversary in between you who prevents your message from writing to the chain. Once we have this definition of a public bulletin board, we can talk about the censorship resistance function for the public bulletin board, which is phi here. And it basically takes in the tip T and spits out the minimum bribe it would require for the adversary to make the write fail. So for example, if every time I put a tip of $10 in, it costs $100 to censor, that would be a mapping of phi of t equals 10 times t. But in fact, on a single leader-based chain for one block, that function is just phi of t equals t, the identity function. And so we don't have very much censorship resistance. In other words, more simply, if you put a tip of $10, it costs $10 to censor you. And in order to make the chain good, to make it censorship resistant, in order to do that, we need the censorship resistant function to be much higher than the identity. It needs to be k times t. And in the paper that I was alluding to earlier, we showed that with k concurrent proposers, and you do a little trick with conditional tipping, you can get the censorship resistance function of the blockchain in a single slot to be k times t, which is exactly what I said we wanted earlier. And once you do that, the rents that the proposer is able to grab, the MEV goes down by a lot. And the intuition for this is basically the more proposers you have, the more paths you have to get on chain. And in order to stop them, you have to bribe each of the proposers. So how do we actually do this? Because this sounds like a pretty complicated problem. I actually talked to a bunch of ConsenSys experts. I said, can you give me, I'm a game theorist, so I talked to ConsenSys experts, and I was like, can you give me something that has these properties? And they're like, that sounds really, really complicated. That sounds like something we probably can't do. And then Malesh was like, what if we just ran a bunch of chains in parallel and merged them with the execution layer? And then they tried to break it for a really long time, and they couldn't break it. So we were like, maybe this works. So then that's how we started working on this paper. There's two ingredients for that. There's this delayed execution, which is how do we go from the transactions that we get from the multiple proposers to an actual execution block? And then there's, how do we get the multiple proposers each able to have an opportunity to include transactions on the chain? So here's an approach that we also explored. You could run LMD Ghost, which is the Ethereum consensus mechanism. You could try and run that and just have a bunch of proposers adding onto it. So it's kind of looks good, and maybe if computers had infinite memory, then this would work pretty well. But you actually get this huge potential for forking, and so the adversary can create this situation where the fork choice tree that's held in memory in each of the validators grows large, and it grows too large to basically store in memory. And then another proposal was Mysticetti. There's a few wrinkles with Mysticetti. One of them is that it's kind of an asynchronous design protocol, and so the slot time isn't as concrete, and there's some interesting wrinkles around MEV for that. And the other one is that it's limited currently in how many attesters it can handle, which of course would be a non-starter for putting on ETH. So here's an illustration of that kind of fork choice situation. Because there's multiple proposers, each of them can fork the chain, and so the probability that an adversary can make the fork choice grow very large in a short amount of time is quite high. And you can see that illustration here on your, I don't know, your left or right or whatever. So here's an illustration of how BRAID works. We don't do that. We actually quarantine each of the proposers to their own subchain. And that makes them unable to create this fork choice problem. Basically, they can only fork their own subchain. They can't fork the whole view. And it turns out quarantining that prevents this unbounded tree size attack, which would like break the chain, basically. And the way it works is basically each chain runs something like LMD Ghost or Goldfish or one of these slot time protocols. And then we look at all of the blocks that came in slot 3. We take all of the transactions from those blocks and we merge them together into one set of transactions. So here's just a more formal way of saying that. You run k parallel chains. All chains are synchronized, which means that the slot times are the same across all of them. And the block in slot I is the union of all transactions in slot I on all k chains. And then what do we do with that? Well, we have to order those transactions because there's a ton of different transactions. Some of them may be overlapping, some of them not. We have to find a way to weave those transactions together. And there's a few proposals for that. One of them, which I think is a pretty good and very simple rule, is this decreasing priority fee order, which I showed earlier. And the advantage of the decreasing priority fee order is that the apps can read the priority fee. And so the thing that they called MEV taxes is basically the app reads the priority fee and charges an additional premium on top of the priority fee. So for example, a AMM might charge you 90% more on top of your priority fee. So they're charging like 10 times more than the priority fee to access their state. And that means that they can capture that 90% basically. And once you have censorship resistance with BRAID, you can get a bunch of great properties from this. Another one, there's this kind of more complicated, more formal knapsack maximization over the set of priority fees, basically. But you can do an arbitrary objective function there. And then there's this execute as needed application-specific sequencing or execution flags. I tried to call it execution flags, but then Yuki from Sorella decided to call it ASS, which is application-specific sequencing. So I lost the battle on the naming of that one. Anyway, so a few straightforward properties. You get liveness from the liveness of each of the chains. And if you have eventual consistency on each of the chains, then eventually the shared view of all of the chains is eventually consistent too, but you just wait for the slowest chain. And once that's eventually consistent, you can finalize it with a finality gadget, and you can compute the state root. I have 1 minute. Let me go into some details. So there's a few optimizations we can do here. In this, we have a bunch of separate blockchains running in parallel. So we can actually aggregate the votes from all of them and make them be a single message. That reduces the communication complexity. It also gets in the way of a few nasty timing balancing attacks that can happen where you try to like delay your vote on one chain and see what happens on the other chains. So that timing attack is kind of negated by this one vote for all of the chains. And then there's a few drawbacks. I think it's potentially an all-pay auction in these first price. Right now we have this first price combo knapsack that the builders run. All-pay auction might be a little bit worse, which is what you might get out of the priority fee auction. And there's transactions that might be added to multiple proposers' blocks. But on the upside, we basically solve MEV. So I would say that's a pretty good trade-off. Basically, we can stop leaking $600 million a year to the proposers by doing this. All right, that's all I had. Hopefully we can solve MEV together.